Hello, everyone. My name is André Codesso dos Santos. I am from Brazil, and my presentation here today has this title: The Sonic Domain Theory Perspective about Time in Music, Sonic Time, Sonic Space, and Perturbation. As a composer and music theorist, a question has been guiding my endeavors. The question is how to understand and measure time and space in music, and how does this understanding affect my compositional and analytical processes. Several music theorists and composers already had given some answers to that question. However, and almost every approach about time in music are related to the question of how do we perceive time, which is essentially a cognitive issue. However, what has been driven me to this point so far is not mainly how we perceive time, but how can I model time and space in music. In simple words, my work consists of building a theory which I call the sonic domain theory, based on a philosophical approach to time, which allows me to compose and analyze music. My work here today is talk about three concepts. These three concepts, they are the sonic time, the sonic space, and perturbation. So this is a very mathematical approach. It's a philosophical approach as well, because I am trying to model music time. So to do that, I have to understand, or at least I have to propose a concept about time in music, space in music. And from now on, when I say sonic time, I am talking about timely music under the sonic domain theory perspective. When I say sonic space, I am talking about musical space under the sonic domain theory perspective. And that being said, I would like to briefly talk about these concepts with you. So, Rudolf Carnap, which is a very known scientist, philosopher, has a book, The Philosophy of Science. And in this book from 1966, he has these three laws, which are very important For me, he says about additional law, unit law, and equity law. Carnap is talking about measurement of time, or how can we measure time. So you can think about how measure time using this addition law, unit law, and equity law. Another philosopher that is so important for me is Hans Reichenbach. He was a German philosopher who lived in United States in the 40s, 50s. He has a very important book from 1956, which is called Time Direction. He has these two great ideas about direction and causality in time, which is this relation bigger than, or less, or smaller than, to arise order between things in time. When we look for something in nature, we all can observe relations of before of or after of. And these relations together gives us direction of all these events in time. So Carnap talks about time measurement, and Reichenbach talks about direction and causality. We have Hawking, which I am not good enough to talk about all Hawking's researches, but you all know Stephen Hawking. And he talks about this concept, arrow of time, which is the events always can go to the future. You cannot go to the past, which is the entropy. You all know which is entropy. But for me, these two philosophers, Carnap and Reichenbach, are on the very basis of the sonic domain theory. So we can go from this to another work. Lee Smolin He is a Canadian physicist. He is a very prominent physicist at the Perimeter Institute in the United States. And he has a book from 2013, which is called Time Reborn. And Smolin, he has these two very important concepts, which is emergent time and non-emergent time. Emergent time is that time that emerges from space, which is the, the perception of time that we have when we measure, for an example, how much long it will take for me to go from a point A to a point B. And that time emerges from the space. And the non emergent time, according to Smolin's approach, is actually the real time that is not possible to be encapsulated by non mathematical models. This is a very bigger and deeper question for physicists. It's not for me because I am not a physicist. I am musician and a composer and a mathematician. For us, and especially for me, this concept of emergent time is very important because I believe that is the case of music. In other words, the sonic time is a sort of emergent time. The sonic time is a kind of emergent time that emerges from the musical space. So we can say that sonic time is a passive time, and we can say that sonic space is an active space. I'm sorry, here is wrong, right? It's not sound space, it's sonic space. I'm sorry for that. So that is core of the concept of sonic time. When I say that the sonic time is an immersion time, I'm also saying that this time can be encapsulated by mathematical models. And when I say that this time emerges from space, I am not saying only the score is a space. I'm saying that consciousness is sort of a space. The score, the paper is a kind of space. A hall of concert is a kind of space. A recording is a kind of space. In my thesis, I talk about this all kinds of musical space in a deeper way. So, with all this in our minds, let's move on. Xanax has another kind of approach to time. I have interest in this out of time concept and this in time, which can be explained on these two figures here. So in the left side of the screen, you can see an event A, and then which is a sequence of single notes, right? And a event B, which is a chord. At the bottom, you can see event B and then the event A. I say, as Xenax proposes, these events are out of time because they have a lack of global order and direction, despite they have a internal direction and order. When you see to this event A right here, you can see a little bit of order inside of this very small element or event. But in terms of global order, they have not, because I can say, or I can put A then B or B then A. It doesn't matter because they are out of time. And Xanax has this other concept, which is in time, where things and all events has global order and direction defined by causality, which is, if you remember, what Reichenbach was talking about. So when Xanax talk about in time, actually he's taking all Carnap's definitions and all Reichenbach's definition, because here when things has global order and direction, you have order, global order, direction, and you have causality, because you know who comes first and who comes second. In other words, who is after and who is before. And you know who is the bigger one or the smaller one, or who lasts more and less in terms of time. So I can put some definitions. So the first one is time in music always emerges from space. That's the definition of emergent time from physicist Lee Smolin, which I take as a foundational basis for the sonic domain theory. I can move further on two major assumptions. The musical score is a sort, not the only one, but a sort of space that captures time. Events on the musical score can be mathematically described because when things are in time, I can say who comes first, who comes in second. All these relations that Reichenbach and Carnap and Smolin are saying are present on the score, which is a sort of space. And sonic time is emerging from that space. Talking a little bit more about the sonic space, I would like to briefly talk about the topology of sonic domain and the abstract surface of the sonic domain. Let's say that horizontal line is the surface of the sonic domain. And let's think about these two vertical lines here. You have three different phases, right? This first one, this second one, and this third one. The topology of the sonic domain is the place where the surface arises, which is an abstraction for understanding what is the sonic space. In the first phase, you have events with no quality. In the second phase, you have events out of time, as Xenax is proposing. There is no global order, there is no global direction, and there is no causality. So in this final phase, you have all things in order. I mean, you have order, direction, and causality, all things working together. This is another way of seeing this surface. Here you have a three-dimensional way of thinking and visualizing what I'm talking about. I know this is very abstract. This surface here, it's where things are happening musically. And this is the surface of the sonic space. But all of things, all of this, the deeper levels and the surface level, all of this is the sonic space. Now I can talk a little bit more about perturbation. We have here two samples. The first one is Verber's Opus 11 for cello and piano. Here at the bottom of the left side of the screen, you have Bach's Prelude number 2. Let's hear a little bit. So let's hear now Bach's Prelude number 2. What I'm talking and what I'm proposing is this first example, the Webern's Opus 11, has a strong periodicity, and the second example has a weak periodicity. This occurs because if you look to the events, you see this note here is it's not the same as this. I am not talking about pitch. I'm not talking about dynamics. I'm talking about rhythm and how much long takes this event here. So this is different than that, which is different than that. These two are equals. This event or this point of attack is very different of this. So What we have here, we have the relation of bigger than, smaller than, relation of after and before them, much more stronger than on the second example, because they are all different. So because of this difference, we can measure time, we can feel direction of time, and we can perceive order and causality of things in time. So because of that, we say that we have a strong periodicity. So it means that here the level of perturbation is higher than the Bach's example. Why is that? Because the periods here is stronger and the periods here is weaker. When you look to the Bach's example, again, I'm just talking about the rhythm, okay? All are the 16 notes. You see 60 notes, 60 notes, 60 notes, 60 notes. You will have the same note after the same note. So when you have no difference between things, you have a weak periodicity. So for me, this is a lower level of perturbation, and so for this, perturbation is the similarity or dissimilarity between space variation as a function of time. This is a very mathematical concept. I bring to you another example where we have no perturbation. This example on the right side of your screen is a minimal perturbated space because all notes are the same. And now you can think in other parameters. The pitches are the same, the dynamics are the same, and the rhythmic figures are also the same. This little example here has zero perturbation because there is no difference between all or any events, which means that the sense of direction it's not so well defined, which means that the sense of causality is not well defined, which means that the order as well it's not well defined. So good levels of perturbation gives us a well sense of direction, order, and causality in music. I would like to finish my presentation just showing to you a few samples of analytical tools that is based on this very notion of perturbation and also sonic time and sonic space. Let's, for an example, take this sequence of rhythmical figures here. We are starting here with this half note. When you look to this two-dimensional graphic, you can see on the y-axis, which is this one, all events. I'm calling events this point of attack, okay? And on the x-axis, time in seconds. So you can see here the first note is during 2 seconds, and then I have this line here. And this is the mathematical model. Here you have two notes, 280 notes, and the line is different now, is in orange. You have a shift of the angle of the line. You can perceive that. On the yellow square, you have this triplet. Again, you have another shift on the line, and then you have the sixth note and another shift on this green square. So all these shifting points for me, it's what I call index of perturbation. So now I can see on a graph how much is perturbated my music or the music I am analyzing. Of course, I am talking here about just a linear perturbation. Why this name? Because I am just analyzing one single parameter, which is the rhythm. But I can, and I also have another graphs to analyze at the same time 3 or 4 parameters with the same concept of perturbation. From the analytical point of view, I think it's very important to see how are the behaviors of some pieces considering this level of perturbation. As a conclusion, I would like to say that the concept of the sonic time and the sonic domain has positive operational features. It means that I have been using to analyze a lot of music and publish papers here in Brazil. The second conclusion is the perturbation can be applied as many parameters as required. So I can apply this concept of perturbation on dynamics, on chord progressions, because perturbation is essentially the shifting of a pattern. So I can apply this in many parameters as required. All analytical tools can operate in a different aesthetics. It's very important to say because I have been conducting some analysis on popular music, and the sonic domain theory is still evolving. So, if you want to talk and get in touch with me, it will be a pleasure to do it. So you can do this through my website, André Codeco, altogether, andrecodeco.com. Thank you, guys. Thank you. Bye bye.